Okay, everyone, thank you so much for coming. And by everyone, I mean the 37 people basically on Zoom, and then almost a full house. This is exactly what I like to see. Marty has been basically in the group for 5 or 6 years, and this is exactly the sort of turnout that we want to see at an event. So thank you all for coming. I had in my mind prepared probably close to 5 minutes worth of remarks, but I promise I won't go that long. So I have a lot of things to say about the very special place that Marty holds within the Kempa family. So to begin with, I'd like to start out with a kind of a brief discussion of her science. So I want to start with the science. And the simplest way I can describe it is that she's found clever ways of taking old materials and having them do or play interesting new tricks. So she's taken an old material and found clever ways to make it to perform new tricks. And these new tricks, so I guess I have a question. Does anyone know what a Polaroid is? Who doesn't? Okay, then you have to leave the room. So a Polaroid is just an old-fashioned, basically, form of film. And the active ingredient within that film, within that photographic emulsion, is silver bromide. And essentially, I don't know, please come on in. And what Marty has done in her research is essentially, again, she's taken an old material and found a way through chemical means to make it much smaller. And then to take these really small particles of silver bromide, dress them with molecules, and then introduce a base, which is another molecule, in the presence of basically light. And she found that you can take these little tiny particles, so-called nanoparticles, and turn them into dumbbell shapes. And it turns out that these dumbbell shapes have really interesting properties. But then she wasn't content with just making a cool thing. She actually spent 2 years of her PhD trying to figure out why these things grow the way that they do and what sort of properties they have. And basically what she found is that, again, as I said, these particles are dressed with molecules, and you need to displace some of these molecules in order for another molecule to come in. It sounds very simple and very easy. You could probably sketch it out on the board. But again, a PhD takes 2 years essentially sometimes to figure out or at least this part of the PhD took 2 years just to figure out. So it's really impressive achievement. So she made a new thing. She figured out why it grows the way it does and what interesting properties it has. And then not content with that, she then tried to figure out what it could be used for. And in this case, so we surmised a few years ago that we could take this sponge-like matrix or lattice of the silver bromide and shove some more ions inside of it. And then do essentially the same chemistry that she developed early on in her PhD to figure out that you could actually grow alloys. And then these tiny little nanoparticle alloys turn out to be really good catalysts. So for those of you that don't know what a catalyst is, it's basically a thing, a molecule, a chemical that converts one thing into another thing very efficiently. And in this case, these catalysts in the right formulation or right composition can take CO2, which is bad, and convert it into CO, which is a relatively less bad but more useful compound or molecule. So she's done all of this, right? It's very impressive. So that's all about her.
Do you want to solve for me?
I've left out a lot of important details. So that's all her amazing science. But I can't stop and let her talk without talking or speaking to her basically attributes as a person. And, you know, a lot of people in science just say that the PhD process is kind of like, you know, the student's process and the student's journey with just the PI at varying degrees of serving as in varying degrees as a guide in the process. And anyone that knows me knows that I get very involved with my students. But I actually think that this is a somewhat of a simplistic notion because in reality, the best science and the most special science happens when the PI and the student are actually engaging in that journey together in a really meaningful way. And as we all know in life, the most satisfying journeys are the ones that you take with best friends or good friends and people that you know are smart, are dedicated, are resilient. And we all know just that Poles are probably some of the most resilient people on the face of the planet. Come and fight me if you disagree. And then finally, you know, it's great to take these journeys with people who you always know have your back and you have their back in return. So for all of these reasons, both the scientific and the human and everything in between, this is why she's going to be very sorely missed from our group. And before the waterworks start, I'm going to stop and I'm going to let Marty talk about her research.
So plenty of time for waterworks later. All right, thank you so much, Tom, for that beautiful introduction and for introducing my work so nicely. And thank you again for being here. Come on in. It's okay. And to those zooming in from home and work as well, I'm very overwhelmed by the show of support. So please bear with me as I try to get through this. I'm really excited to share with you a little bit more about what I've been working on over the last few years, namely my thesis project focused on host-guest mediated approaches for the synthesis of functional multi-component nanostructures. So today I'll tell you about multi-component nanostructures, what they are, how they're made, and what they can be used for. I'll talk about a specific technique that we can use to make these multi-component structures called host-guest synthesis. I'll go into detail about how we use the aspects of host-guest techniques to derive our own multi-component silver-silver bromide dimer nanoparticles by way of a silver bromide host. I'll go into details about the properties of those dimer products, as well as the mechanisms of their formation and the formation of that silver bromide host. And lastly, I'll talk about how we expanded our ability to use that host-guest technique to a different set of materials to yield an even different product, silver copper alloy nanoparticles, and I'll talk a little bit about their catalytic activities and what we can use them for. So human beings are intimately aware of what multi-component architectures do. We see how multi-component structures function every single day. Kids like my nieces and nephews who are here with us today play with Legos and create new structures like castles. We use bricks, lumber, and other materials to build buildings like those beautiful row homes that we see down in Fells Point here in Baltimore. And we also build fast-moving vehicles out of thousands of tiny components. So in all of these cases, no matter the example, the individual parts and the interactions between them contribute to forming a larger structure which performs some desired outcome or function. Now, it's one thing to be able to build with Legos and bricks which we can hold in our hand, but it's another feat entirely to be able to do that on the nano scale, with building blocks roughly 1 billion to 1 million times smaller. But what if I told you that that is indeed possible? Well, it absolutely is. On the nano scale, we have what we call multi-component nanostructures. So these materials range from 1 to 100 nanometers in diameter. They're comprised of 2 or more domains, and those domains or building blocks, like Legos or bricks, are joined by precise junctions, what we call interfaces. So even on this small of a scale, which you can't see with your naked eye, the careful selection of these components and tuning the interactions between them lets us tune for the overall functionalities of these structures that we yield at the end. And those functions are going to come up a little bit later, just at this next slide. This isn't working, sorry. So there are a number of different ways that we can make these multi-component nanoparticles. We can grow or deposit a secondary material on an existing particle in a process called seed-mediated growth. We can replace some parts of an existing particle in processes like galvanic replacement or cation exchange reactions. We can chemically weld 2 or more particles together to form a larger structure. And we can also heat atomic precursors or collections of nanoparticles and thermally anneal them to form these multi-component nanostructures. With these examples only reflecting a few of the different synthetic techniques out there. So just to go into a little bit more detail about one of these approaches, seed-mediated growth here specifically, is used to create these titanium dioxide capped gold nanorods. So in this particular system, the curvature at the tips of these nanorods makes the ligands or the molecules that stabilize these nanorods less dense. That lower density allows for the TiO2 or the titanium dioxide precursors to come in at the tips, and we eventually yield these gold titanium dioxide nano dumbbells, as they call them, as we see in this micrograph here. So you might be asking yourself, what can we use these multi-component nanostructures for, and why do we care about them to begin with? Well, it turns out that they can be used for a number of different applications. Building a nanoscale photocatalytic reactor like the titanium dioxide gold dumbbells that I just talked about could have enormous benefits for turning waste products into useful chemicals simply by just irradiating them with the sun. Multi-component nanoparticles can also be used in biomedical imaging, for example, to earlier detect cancerous tumors within the body. Other possible applications include using these multi-component nanoparticles for drug delivery in physiological systems. There's also the idea of using them to burn away cancerous tissue underneath the skin in processes called photothermal therapy. And I just talked about how we can build very small multi-component structures. In a very sci-fi way, we can also miniaturize robots or motors on the basis of these multi-component systems. So although many examples of multi-component nanoparticles exist, with those that I just highlighted only representing a small fraction of what's in the literature, the methods used to make them are not without their limitations. So one of the major limitations is that one method might not necessarily be applicable to a broad range of materials, or it's only applicable to a small set of precursors that you can use to make these structures. Secondly, some of these methods just aren't really good at making precise interfaces or junctions between the building blocks that make up that multi-component structure at the end. Some of these methods also aren't good at controlling the size and shape of the products that they yield. And lastly, a lot of the methods just don't make enough of this product to be industrially relevant or scalable to the point that you can use it in a larger application. So at this stage, I'd like to introduce a slightly different technique that we haven't yet talked about that can also be used to make multi-component nanoparticles, called host-guest synthesis. Host-guest synthesis can be broken down into three broad categories. In the first, nucleants or reagents for a particular process are harbored in the pores at nanoscale volumes of a host, and in those pores, they interact to form that secondary material. In the second category, the host is consumed during the formation, and all we have left at the end is that secondary material that the host was used to make or create. And in that third category, the host survives the process, a secondary component is extracted out of the host in some ways, and that host remains as part of that multi-component nanoparticle at the end. So host-guest techniques address a lot of the synthetic challenges that I just mentioned a few slides ago, and one of the most outstanding ways in which host-guest chemistry helps address these challenges is by localizing those reaction precursors to a very small nanoscale volume, which then gives you the potential to create atomically precise interfaces between those building blocks, and also allows you to exploit concentration gradients that are not mirrored in the bulk on larger length scales in these materials. So we use the basis of host-guest interactions and put the advantages of this technique into practice and developed a new synthesis to make multi-component silver-silver bromide dimer nanoparticles. So our host-guest approach involves using silver bromide nanoparticle intermediates as platforms for the formation of that final heterostructure, that silver-silver bromide dimer. So the formation of the silver phase of this dimer occurs when we expose the silver bromide host to external stimuli, which is what we call the dimerization process, so that will come up again in my talk. And that process is when we expose the silver bromide to UV light in the presence of a molecular reductant, L-arginine. So in this way, we use the silver bromide host to create these dimers by way of that third category of host-guest syntheses, surviving host processes. So we can monitor this dimerization or formation of that dimer process by optical characterization of the host nanoparticles before they're exposed to UV light and L-arginine, as well as the products after exposure. So we see an obvious color change in the solution before and then after exposure. So the silver bromide host nanoparticles exhibit this gray color, and after we dimerize them, they have this purple solution color. This change in solution color corresponds to a change in the UV vis profile of these species, with the growth of two new features in the absorbance spectrum of the dimers, here with a peak at 370 nanometers and a longer wavelength peak centered at roughly 550 to 650 nanometers once those dimers are formed. We further confirm that the dimers are only formed after that dimerization process is initiated or the UV light and L-arginine is introduced via powder X-ray diffraction studies of a sample of these silver bromide hosts. So in this data, we see that there are no peaks. So these blue peaks corresponding to metallic silver are not present in the data for the silver bromide hosts. This indicates to us that we have a clear two-step synthetic process, and the silver bromide is acting as a true intermediate. Only when we controllably expose those hosts to UV light and L-arginine do we get those silver-silver bromide dimers at the end. So we then went on to characterize the structure of the dimers that we yielded via transmission electron microscopy, or TEM, and scanning transmission electron microscopy with energy dispersive X-ray spectroscopy. It's a bunch of words. Just look at the acronyms for them. I promise they mean the same thing. So EDS mapping here showed that the dimer products are made of two distinct phases. Here we see the silver corresponding to the green in that silver phase, and the red color corresponding to the bromide in the silver bromide phase of those dimers. The phases are also joined by an atomically precise interface, as we see in the STEM hat of data here. And they're fused by what we know and has identified to be the 111 facet, which is a key feature of the system that's going to come up a few more times in my talk today. So after having characterized the host particles as well as the dimer products both optically and structurally, we were interested in further probing some of the properties of these materials and figure out if we could do anything interesting with them. Specifically, we were interested in that feature that I mentioned just earlier in this absorbance spectrum, that distinct optical profile of the dimers compared to the silver bromide host nanoparticles prior to irradiation in the presence of L-arginine. So we know that a single isotropic metallic nanoparticle like silver, when I say isotropic, I mean symmetric all the way around, when it's irradiated with light, will have an absorbance profile with a frequency and therefore wavelength corresponding to its plasmon resonance. Now, when the dielectric environment of that isotropic nanoparticle is altered, perhaps by introducing some sort of differential ligand coverage or bringing a secondary material close to one of its facets, the frequency or wavelength of that plasmon will be altered, which is denoted here by that different color of arrows that represents that plasmon frequency. If you change the shape of the particle altogether and have sort of, say, something more oblate or oval-like, the frequency of that wave or wavelength of that particle's plasmon is changed even further. So I just gave you a very quick crash course into plasmonics, and we know how the dielectric environment and the morphology or shape of the silver particle can influence its optical profile. But what we were interested in is in determining what exactly is giving rise to these two new features in the absorbance profile for the silver-silver bromide dimers. So to do this, we wanted to determine what aspects or components of the dimer morphology are giving rise to those two new peaks. First, we focused on the interface between the silver bromide and silver phases of the dimer. We're able to isolate that interface by introducing some nucleophilic solvent and selectively digesting away that silver bromide phase to yield a single silver nanoparticle. After we etch away that silver bromide phase, the interface is now exposed. So we compared the UV vis profiles of these species at the three key stages of synthesis: host, dimer, and the particles that we isolate. We saw no plasmon peak for the silver bromide, as expected. Two new peaks in the plasmon profile for the dimer, which I had previously shown you. And when we remove the silver bromide phase to yield that single nanoparticle, we see an absorbance profile that we would expect for a standalone isotropic nanoparticle of this size, with a sharp peak at 405 nanometers. So we recover that plasmon for the silver nanoparticles after removal of the silver bromide phase. So this was our initial indication that the two-peak profile is indeed a result of the presence of the interface in that dimer morphology. We were also able to systematically monitor the evolution of the absorbance spectrum during the etching process by taking timestamp UV vis measurements, and with this further confirmed that the interface is caused by the two-peak profile rather is caused by the interface in these morphologies. So you'll notice that when the dimer is intact, we have that two-peak profile here. There is a peak that we ascribe to the silver plasmon of the silver phase in that dimer, and it lies blue shifted with respect to where we would expect a standalone nanoparticle to come up at roughly 405 nanometers. So this is due to that anisotropic, or in other words, uneven or unsymmetrical dielectric environment that that silver particle is facing or experiencing with the silver bromide on one of its facets. When the etching process continues and that silver bromide is removed, we recover a uniform dielectric environment, so symmetrical all the way around that silver nanoparticle. The plasmon peak shifts to a higher wavelength or lower energy, and again corresponds with the plasmon resonance for a standalone or a solution of isotropic silver nanoparticles in this size regime. So I just showed you evidence for how the interface between the silver and silver bromide phases of that dimer impacts the plasmon resonance of the silver nanoparticle. Now, in seeking to even more deeply understand the nature and impact of the interface in the system, we sought to controllably manipulate the environment around that silver nanoparticle even further and focused on the 111 facet that made up that interface in the dimer morphology that we know is now bare or accessible. So there are a number of different pathways that we saw we can potentially manipulate the dielectric environment at this facet. We could potentially deposit a new material or grow a new material on the 111 facet, functionalize it or add different ligands to that area to create a dielectric environment that's different here that way, and also potentially coax interactions with other similarly coated silver nanoparticles to get them to make multi-component structures. So we started with that first option, growing or trying to deposit a material on that host, the silver particle at the 111 facet. And we hypothesized that if we added dilute solutions of silver bromide precursors and allowed the samples to sit undisturbed, we call this an incubation process, that perhaps we could deposit silver bromide again on that 111 facet and potentially control.
Yeah, right, Luce. How you doing today?
Anne-Marie, can you please mute yourself? This happens sometimes, it's okay. So we thought that we could potentially grow silver bromide on the 111 facet of this silver nanoparticle, perhaps control for its size, shape, and thickness to be a little bit different than that nice round silver bromide that we previously had, and in that way access some different modal profiles. So it turns out that when we add these precursors or those dilute solutions of silver bromide precursors, let the sample sit undisturbed, we get some silver-silver dimers. So in this case, it's not silver and silver bromide, but two silver nanoparticles that are joined by what we think is a silver bromide net material here. Now these particles make up less than 30% of that final sample solution.
I do have some. And but a lot of people have worse things.
She would check it out. Not that we did, but I never know.
Jeff, that's going to be a funny story for Brian. All right. Okay, so after we added those dilute solutions, we saw in less than 30% of the sample yield these silver-silver dimers joined by what we think is a silver bromide neck. And although they make up less than 30% of the solution, we still saw some differences in the UV-vis profile of these samples. And it's interesting to note here that these absorbance profiles feature a peak that is blue shifted or at higher energies compared to that silver plasmon at 405 nanometers. So this is expected for two plasmonically active metallic nanoparticles that are in close contact. According to plasmon hybridization theory, when you bring two plasmonically active materials in close contact, their plasmons hybridize or combine to form these higher energy hotspots in those interparticle regions. So these experiments, although super preliminary, were very exciting because they indicated to us that we could potentially yield silver nanoparticles that we can directionally control their interaction with others from that host guest technique, and in that way, engineer some different plasmon modes in a sophisticated way. Get back on my flow now. So up until now, I have described how we successfully synthesized silver bromide dimers by way of a silver bromide host, and also probed some of their interesting qualities. We also investigated the mechanisms of formation of that silver bromide host intermediate and the dimer products, in search of a deeper understanding of how all of the components of our synthesis are interacting, to be able to then maybe selectively alter the interactions between those components and make the overall synthetic technique applicable to other materials and make other products. So to probe this mechanism, we first wanted to understand and confirm the role of the oleate ligand in our synthesis by looking at the impact of solution pH on the products that we yield. So at acidic conditions, or at pH lower, more acidic than approximately 9.2, which I highlight with this red box here, we see a drop-off in the number of target dimer products, denoted by this blue line. So we see that drop in the number that we count, and a higher number of byproducts like clusters of silver nanoparticles, silver bromide multimers, and dendrites that are super susceptible to reduction when we look at them in the microscope. So we posit that at these acidic conditions, the sodium oleate, which is stabilizing that silver bromide host, is protonated at that carboxylate moiety, which it uses to interact with the surface of the silver bromide nanoparticle. When you put a proton there, it can't interact with that surface and therefore effectively stabilize those host morphologies. So that lack of stabilization results in more promiscuous nucleation events. We no longer have that single symmetry breaking event that causes that silver bromide dimer to form. And all of this data collectively showed us that the oleate is necessary to stabilize the spherical silver bromide dimers, and in that way also propel the growth of those isotropic or two nice phased silver bromide dimer products that we get at the end. Having established the necessity of the oleate ligands to the stabilization of those hosts, We then moved on to investigate the mechanism of how the dimers were formed and asked ourselves, how fast do these dimers grow? And what is the timing of this process overall? So we found through carefully running these experiments, stopping them at 1 second intervals and taking a look at the products via UV vis and under the transmission electron microscope, that this process occurs over a time scale of roughly 6 seconds and in 2 very distinct phases. So in that first phase, over the first 1 to 3 seconds, the silver bromide host turns from spherical to this cubic silver bromide morphology, and that process is independent of the presence of L-arginine, so it's strictly a UV-induced process. Whether or not we have that molecular reductant there, first 3 seconds, we get a silver bromide cube. 4 to 6 seconds, or that second phase of the growth, the silver phase grows out of one corner of the silver bromide, the silver bromide cube starts to contract and form a sphere, and then we eventually get this 2-phase silver-silver bromide dimer as our product. These experiments also indicated that this secondary process, or that 4 to 6 second growth, is dependent on the presence of L-arginine in the system. So L-arginine is necessary to initiate that symmetry breaking process and create those silver-silver bromide dimers at the end. So having established the importance of oleate, as well as the importance of L-arginine in our system to drive the formation of those dimers, we then investigated the role of other ligands on the surface of these hosts and how they impact the synthetic process. So the next puzzle piece that we wanted to sort of figure out was what the ascorbic acid was doing in our synthesis specifically. So in our silver bromide synthesis, ascorbic acid is not acting as a reducing agent, as it commonly does in noble metal nanoparticle syntheses. So again, this is demonstrated by the lack of PXRD peaks corresponding to metallic silver in the samples of these silver bromide hosts. It seems, though, that ascorbic acid is working with the oleate ligands to stabilize the silver bromide nanoparticles and controllably direct their growth to form these spherical host intermediates. So if we simply just eliminate ascorbic acid out of our synthesis, we don't get spherical silver bromide, we get these silver bromide dendrite antler-like species. They're highly susceptible to reduction in the electron beam or under the transmission electron microscope beam, which indicates to us that there's just not enough stabilization occurring there without the ascorbic acid. So we know ascorbic acid is not a reducing agent, and it's necessary to yield spherical silver bromide particles. So we hypothesize that it's acting as a co-ligand with the oleate to form the stabilizing ligand shell. We also know that this idea of a co-ligand system in nanoparticle syntheses is not unique to our process. The use of combinations of ligands to control the shape, size, length of different nanoparticles very elegantly is a concept extensively explored in the literature, just like the CTAB and sodium oleate combination that's used to tune for the aspect ratios of both nanorods in a very nice and beautiful way. I wish I could make nanoparticles these beautiful. So to test this theory that ascorbic acid is acting as a co-ligand, we figured that we should also be able to make silver bromide host nanoparticles that could work or sort of function as the producer of the silver bromide host if we switched out that co-ligands for analogs of the ascorbic acid. So we synthesized silver bromide with 2 analogs, salicylic acid and diethyl dithiocarbamate, which I will not keep saying in this presentation. I'm going to refer to it as the carbamate moving forward. And we saw via PXRD and TEM investigations that no matter the co-ligand that we use, we're able to form spherical, well-stabilized silver bromide host nanoparticles. We also hypothesized that these co-ligands may act as a defect point in that ligand shell. So not only are they existing as a stabilizer, but they might be gating the association of the L-arginine, which we previously discussed was very important and necessary to the formation of our dimers, to the silver bromide surface. And to test this out, we turned to Fourier transform infrared spectroscopy, or FTIR. We use this technique because thankfully all of these co-ligands have diagnostic peaks that are very far away from the oleate molecules that are in excess in the solution. So it was easy for us to be able to track their presence as well as their disappearance using this method. So using FTIR spectroscopy, we can visibly track the displacement of the co-ligands when we introduce L-arginine into the solution. Specifically, we monitor the growth of the FTIR peak that corresponds to the L-arginine here at 1652 wave numbers roughly, as well as the concurrent disappearance of the FTIR peaks corresponding to those ascorbic acid, salicylic acid, and carbamate ligands, respectively. So we see through these experiments that it only takes roughly 4 microliters and 3 microliters of L-arginine to be introduced into the solution to effectively displace the ascorbic acid and salicylic acid, respectively. And this confirms the likelihood that in our synthesis, where we introduce a lot more than 4 microliters of L-arginine, that process is exactly happening, where the L-arginine is kicking out the ascorbic acid, and in that way functionalizing the ligands, acting as a functionalizing ligand to drive that silver-silver bromide dimer growth. We also see that the L-arginine doesn't as effectively kick off the carbamate. It takes roughly 15 to 20 times higher volumes to kick off the carbamate ligand, and this is likely to some of the functional groups that the carbamate uses to associate with the silver bromide, making them more strongly associated to that silver bromide nanoparticle surface and harder to kick off. So next thing that we did was to confirm that the L-arginine is only displacing the co-ligand in that system and not interacting with any of the oleate that's also on the surface of those nanoparticles. So we performed experiments to quantify the amount of L-arginine left over in solution after some of it has interacted with those co-ligands. To do this, we introduced ninhydrin, which is a molecule that reacts with L-arginine to form a chromophore with a well-known UV-vis absorbance that can be monitored, and then from that UV-vis we can make a calibration curve. So using that calibration curve, we corroborated the amount of L-arginine that was actually associated with the surface of those nanoparticles via FTIR. So those values were also reflected in these experiments. So in other words, let's say we introduced a molar equivalent of 20 microliters of L-arginine into the solution. We know from the FTIR experiments, it only takes 4 microliters to displace the ascorbic acid. The absorbance of the L-arginine in that solution will correspond to 16 microliters, or 20 minus 4. Simple math there. So just to recap all that I've told you about the mechanisms of the silver bromide and silver-silver bromide dimer formations, we have shown that the oleate ligands are necessary to stabilize the host nanoparticles and also drive the formation of those dimers. We know that L-arginine is necessary to drive the formation of that dimer product. Without L-arginine, all we see is a change to that cubic morphology of the silver bromide host. Only when we introduce L-arginine do we get the propagation of that initial silver nucleate and the formation of that silver-silver bromide dimer. Ligand titration studies, again, also indicate that the co-ligands on the surface act as gating ligands for the association of L-arginine. When we introduce L-arginine, it kicks off that gating ligand and is therefore able to associate with the surface. As the L-arginine performs reduction of the silver cations present on the surface of the particle, they start to form an initial precipitate or a nucleate, and as that nucleate continues to grow and silver cations continue to get reduced, there is a continued depletion, saying continued so many times, of the interstitial silver cations from the host lattice to the surface where the L-arginine is, which drives continued growth of that silver phase. So having spent all of this time trying to understand how these particles form and discovering that the process is surface specific, that process being the formation of the dimers, and also we think robust to any species that we can effectively harbor within that silver bromide lattice. If that species can also make its way to the surface where the L-arginine is, it can hypothetically undergo concurrent reduction with the silver cations and form some sort of other material. So we asked ourselves, can we introduce an additional cation into the silver bromide host particles and eventually yield some silver X silver bromide dimer, where silver X here is an alloy of silver and some prescribed element of our choice. And we tested this hypothesis by using silver bromide host to successfully synthesize silver copper alloy nanoparticles. So we did so by simply introducing copper cations into the reaction solution to form these silver copper bromide hosts. Those silver copper bromide hosts underwent the same dimerization and etching process that I've described so far, forming silver bromide silver copper dimers. Then we can isolate the silver copper alloy nanoparticles from that system, again, by selectively etching away the silver bromide phase of the dimer.
The kids, I know.
Okay, so we're able to tune for the amount of copper that we incorporate into the system by simply adding different amounts of copper cations into the synthetic scheme or the process at the beginning of the reaction to achieve nominal loadings of 0 to 15% copper. And nominal here, again, is also a keyword that we will revisit a little bit later. So we characterized the products that we were able to yield from this reaction across that 0 to 15% copper range using TEM. And we saw that independent of the amount of copper that we introduced, here going from 0 to 15% copper nominal loading, we are able to yield spherical silver copper alloy nanoparticles. We do see a slight decrease in the diameter of those silver copper alloy nanoparticles when we increase to the higher limit of 15% copper. And this is likely due to some strain effects as we introduce more amounts of copper, which cause smaller and rounder silver copper nucleates to form on the surface of that host. We also characterize the products optically, as we have in an analogous way to the previous part of the discussion, and saw again 3 distinct profiles for the silver copper bromide with no plasmon peak, the 2-peak profile for the silver bromide silver copper nanoparticles, and again the recovery of that plasmon as we actuate the silver bromide phase of the dimer. So even if we introduce copper, with this data here indicating what we see for 5% copper and silver alloy, we still have those very distinct plasmon profiles. We also showed that we can scale up our synthesis and still see that 2-peak dimer profile after exposure to UV and L-arginine, even if we increase the solution volume to 10 times with that reaction volume. And when we etch away the silver bromide, again, recovery of that silver plasmon peak. As we look at the plasmon peak position over that 0 to 15% copper range, we see that there's very small shift, only about 3 to 5 nanometers as we go to higher percentages of copper. This lack of very noticeable or appreciable shift indicates to us that we're most likely forming very dilute copper and silver nanoparticles, which again, I'll also revisit in the next stage. So this all indicates the retention of this plasmon peak, that these materials are stable to oxidation, they don't undergo any morphological change when we introduce more copper, or they don't undergo any aggregation, and there is also no phase segregation into copper-rich or silver-rich areas. We also see that lack of segregation with increasing amount of copper when we look at the structural effect of the increased copper in these silver copper alloy nanoparticles. So specifically, again, we were very interested in determining if, when we get to that 15% upper limit, do we see any phase segregation of the alloys into copper-rich or silver-rich components, or do we still have that uniform distribution? So we saw through fast Fourier transform derived diffractograms and TEM analyses of these samples that the spots that we see in these FFT diffractograms are consistent with an FCC lattice for silver. And we also see negligible change in the despacing of these products. There are some differences, but they're within the statistical error of our analyses. And all of this data collectively indicates to us that even as we increase the amount of copper, the underlying cubic silver lattice is retained and there's no major structural effect. So we also confirmed the presence of silver and copper in our particles using EDS spectroscopy, and here we see data for a 2.5% copper copper alloy sample. We saw that the silver and copper is relatively well contained within the boundaries of the nanoparticles. It might be a little bit hard to see on the screen, but most importantly, we saw that there's no phase segregation or formation of mainly green and mainly orange portions of these nanoparticles within this data. Every time I go to meet someone, it messes up my clicker. So we then also went on to both qualitatively and semi-quantitatively determine the amount of copper in these particles as we increase that nominal loading. Here we see an overlay of EDS spectral data, which indicates an increase in the relative intensity of the peaks corresponding to copper as we go from 2.5 to 5 to 7.5 nominal copper loading in these systems. We also further confirmed the concentration of copper using ICP-MS and saw that there is an increased calculated percent of Cu as we increase that copper loading. So it's important to note here that the calculated percent is actually a lot lower than what we nominally load. Again, that word comes up. For example, for the 5% copper that we introduce, we only get roughly 1.4% in the actual products that we yield. This is most likely due to loss of copper during the synthetic process. Copper is known to form complexes with oleate, which is, again, excess in the solution. There's also probably loss of copper during the purification steps, as well as some copper being retained in that silver bromide host. It doesn't make its way to that silver copper alloy and therefore lowers the amount that we actually incorporate. Also important to remember that both EDS and ICP-MS especially These techniques are pretty semi-quantitative, and even though our percent copper is lower than what we intended it to be, it's not necessarily a bad thing, which I hope to convince you of in the next part of my talk, where I'll discuss some of the properties of these particles and what we can use them for. So to recap what were presented in this last section, or that sort of expansion of the host-guest technique to other materials, we were able to form silver copper bromide host nanoparticles, and from them derive silver bromide silver copper alloy nanoparticles. The copper interstitial cations hosted within that silver bromide host lattice undergo concurrent reduction in the presence of L-arginine and UV light to form that secondary phase. We can isolate that secondary phase and also tune the amount of copper that we introduce in the solution to get copper at silver alloys with percent copper across this range of nominal loading. So in this last section, I wanted to talk to you about the use of alloy nanoparticles in electrocatalytic applications. So alloy nanoparticles exhibit features caused by synergy or cooperation between their component elements. This might cause optimal surface at ordering, strain and surface defects, and other effects in these alloy nanoparticles, which stabilize reaction intermediates and help catalyze or make reactions occurring at their surface happen more efficiently. So increased interest in industrially relevant electrocatalytic processes has driven efforts to make precise metallic alloy nanoparticles for these types of applications. One of those industrially relevant processes is the CO2 reduction reaction, as Tom sort of mentioned at the beginning of my talk. And it turns out copper nanoparticles are great catalysts for the CO2 reduction reaction because of the optimal binding of the CO intermediate in this process to their surface. However, copper is prone to oxidation. We know what happens with the Statue of Liberty, it used to be bronze, and this hinders its catalytic efficiency. So one workaround, lucky for us, is alloying copper with silver, which is a much more stable material. And in this configuration, we can marry the catalytic activity of the copper with the stability of the silver. And this has led many to synthesize silver and copper containing materials for electrocatalytic reactions, such as silver copper foams, aerogels, nanoparticles, and other structures. However, the techniques used to make these systems are typically very complicated. They require high temperature reduction, multi-step seeded growth, or electrodeposition of precursors that are then sort of embedded in these matrices where we can't isolate those products out from. When we do actually yield well-defined silver copper alloy nanoparticles, those techniques are even more complicated. They're air-free, you have to have rapid shock or thermal treatments, and eventually, or essentially, they're not very scalable for industrial processes. So it's pretty clear that a need for a simple, scalable, and precise way to make silver copper alloys is there. Well, we've demonstrated the ability to precisely and scalably synthesize these silver copper alloy nanoparticles, which addresses some of these challenges that I just presented to you. That tunable copper percentage incorporation is also exciting, as it could give us a lot of insight into the effect of that compositional change on these electrocatalytic processes. So we wanted to see if we could use silver copper alloy nanoparticles for the CO2 reduction reaction. We evaluated the activity and selectivity of our silver copper alloys by depositing inks of these particles onto a porous, conductive carbon substrate, and in that way forming a gas diffusion electrode, or GDE for short. This setup highly improves mass transport and overall catalytic activity compared to the more commonly seen H-cell configurations in electrocatalytic studies. We investigated the catalytic activity of these systems by measuring the Faraday efficiency for the products that they form in the CO2 reduction reaction across this compositional range, so from 0 to 15% at 3 overpotentials or applied voltages. So for those who aren't familiar, the Faraday efficiency is a measure of the given efficiency of a given electrochemical transformation in a process. So it's a ratio of the electrons that go into the system versus how many electrons are actually used to make a specific product. So we saw that the majority product for our process, with the CO2 reduction reaction on our nanoparticles, is the CO product, which are denoted by the Faraday efficiencies for CO in these bars here. We also saw a higher Faraday efficiency as we go to more negative voltages or overpotentials, which is unsurprising. But what is very interesting is that we have the highest activity for the 5%, so not the highest copper content, 5% copper and silver alloy at the middle voltage value, or that moderate voltage value of negative 0.5 volts versus the electrode. We also looked at the selectivity of the CO over the other products that are formed in this system. The largest byproduct that we get is hydrogen. And again, we see that there is a ratio between the carbon monoxide and the hydrogen, with more carbon monoxide, again, unsurprisingly being formed at those more negative voltages. But again, we see that there is the highest suppression of that hydrogen byproduct and the highest Faraday efficiency for the carbon monoxide product at this 5% copper and silver alloy. If we increase at the same voltage to 15% copper, we see a drop of that Faraday efficiency to close to 50%. So we attribute that overall reduction in the performance for the CO product to potentially the formation of Cu-rich phases as we hit that sort of solubility limit of the copper within our systems. So it's clear in the previous studies that the 5% copper and silver alloy is the best performing nanoparticle in our system. Having established that, we then went on to look at the stability of these 5% silver copper alloys. We performed 180 minutes of catalytic cycling and measured the Faraday efficiency as well as the partial current density for these carbon monoxide products over that time, and saw no appreciable drop in that activity or selectivity as we cycled the catalyst over and over again. We also imaged the surface of the nanoparticle substrate both before and after the 180 minutes of catalysis, and that revealed no apparent surface or structural change or visible material loss. So again, not only are these alloy nanoparticles well performing, but they're also stable. We also benchmarked the performance of our 5% copper and silver alloys to other materials that contain silver and copper for electrocatalytic reductions. So our 5% copper alloy is able to achieve competitive Faraday efficiencies close to 84% compared to other referenced examples. But it's important to note that they are able to do this at relatively more mild potentials, where these examples sort of bumping up or a little bit higher than our Faraday efficiency, needing much more negative voltages to be applied. And also, as we saw in previous studies, the nominal copper loading is not what we actually calculate. So we're able to achieve these activities at even lower copper than what we thought, which is super exciting. However, not everything also about catalysis is about efficiency and activity. It's also important to be able to deduce or figure out what components of a structural morphology are causing that electrocatalytic activity to be so high or so low. It's very desirable to have a well-defined product. Our system, outstandingly, has very well-defined silver copper alloy nanoparticles that we can deduce from that post-gas syntheses, and this cannot be said for the other references that I include here. If you don't believe me, read our paper when it comes out. There's a very nice whole section about that comparison. So to better understand the CO2 reduction process that's occurring on the surface of those silver copper particles, we also performed temperature-dependent CO2 reduction reactions at a fixed potential of -0.5 volts. So a plot of the partial current density for the carbon monoxide product versus the inverse of the temperature gives us a slope which corresponds to the activation energy for the formation of the carbon monoxide. And if we plot that activation energy in relationship to the percent copper that we introduce into these alloys, we see that there is a very obvious dip with the lowest activation energy for that carbon monoxide product occurring for the 5% copper sample. So it's likely that this lower activation energy is due to some electronic effects occurring between the silver and copper in these alloy nanoparticles that stabilizes that CO in just the right way to propel its formation as the major product. So to conclude this section, we synthesized, again, dilute copper and silver alloy nanoparticles across a 0 to 15% nominal loading composition range by way of that silver bromide host. We investigated how we could use these particles for the electrocatalytic reduction of CO2. We also investigated their activity as a function of the copper percentage and found that the 5% copper sample is the best performing catalyst in our system. So now to recap and wrap up all that I talked about today. So I started this talk by showing you that we were able to successfully synthesize silver-silver bromide dimer nanoparticles by way of a silver bromide host intermediate. We then talked about the optical properties of the host nanoparticles, the dimers, and the silver nanoparticles that we're able to yield, and talked about how we could use them as a platform for investigating further plasmon tunability and manipulation. In probing the mechanism of the dimer formation as well as that of the host nanoparticle, we found that the reduction processes are surface specific and hypothetically could be used to grow silver X or silver other metal alloys by simply introducing another cation into that host species, which could then undergo concurrent reduction with the silver to form a different material on the surface of that host. We tested that hypothesis and showed that we were able to simply introduce copper cations to then form silver copper alloy nanoparticles with tunable percent composition, and showed that we can use these silver copper alloys for electrocatalysis for the reduction of CO2. So I hope that all I've shared with you today has convinced you that our successful host gas synthesis of multi-component silver-silver bromide dimers and our ability to expand on that synthesis to make a totally different material has shown that we can add this technique to the overall toolbox of synthetic methods used to make precise, well-defined multi-component structures with functions. So continuous improvements of our systems and further investigations into expanding its applicability to other materials will allow us to access even broader ranges of multi-component products, and we could use those products for potential applications in optoelectronics, other catalytic or electrocatalytic applications, and in this way further advance the field of nanoparticle synthesis overall. I'm going to take a drink of water. This is where things get messy. So please bear with me. I'm not going to try to stop it because I know it's going to happen. But before I go into questions, at this time, I'd like to acknowledge some folks who were very crucial to these projects. Didn't even make it through one sentence. I also have to read these because if I try to say it ad hoc, it's not going to work. But I promise you, this is also from the heart. Okay, so past Kempa group members and current Kempa group members here in bold. Dr. Ben Stevens, who I know is on here, Alex Cossack, AJ Patera, Adam Strickland, and Cassidy, who all worked to contribute to the nanoparticle projects. This is so embarrassing. This isn't even like the sappy part. I haven't even gotten to like Morris, and I'm already crying. You've been very, very instrumental to the nanoparticle subgroup, its existence, and the work that I presented today, so I thank you. To our collaborators, Professor Anthony Shoji Hall, who's at a conference right now, Nick Zhang, who is here, and Jack Scow. Thank you for all of your passion and hard work you put into making much of the work presented in this thesis possible. It was really a true pleasure to collaborate and craft such a beautiful scientific story with you. Thank you to Dr. Ken Libby over at JHU's MCP and the folks at the IIC for making a lot of my own data collection possible. And of course, I'd like to thank our funding sources for making this research possible and Tom's hard work in gathering those funding sources. I'd also like to thank my committee members, Professor Art Bragg, who's on Zoom, and Professor Fairbrother here for agreeing to serve as my advisors and always being available with your support and mentorship. To the chemistry department admins, past and present, Megan, John, Jasmine, Claire, Indira, and Jess. Thank you for fielding endless questions, room requests, and handling all the administrative work that makes me and other graduate students able to be focused on their research and the work that we do. To Boris Steinberg, who has retired and is dearly missed, and now Matthew Cordruff, thank you for always making sure our lights are on, our labs are dry, and our instruments are safe. Okay, this next section I have titled Sob Story, so let's get ready. Maxie, I have to cry now, okay? It's okay, Gabby. Back in the fall of 20... You want to come up here with me? It might make me look better. Okay. Back in the fall of 2021, I had the privilege of serving on the planning committee for our second annual Global Doctoral Career Conference here at JHU. Our closing keynote that year shared some advice that has stuck with me ever since. No matter where you are or what you do, find your people. Find the people that lift you up, that make you better, that share your values. And so for this last part of my presentation, I wanted to acknowledge my people, some of the people that I found along this journey, and some who have found me. I'm so sorry. Okay, next. Ben is like so uncomfortable when I would cry in front of him, and he's looking at me on the screen like, keep laughing, it's The lab has undergone a number of changes from year to year. We've witnessed past members graduate and move on to pursue postdocs. That's making me cry. Begin on their career journeys and embark on their own new adventures. We've also welcomed new members who bring their talent and perspectives to the group's dynamic with each new year. Tom has lost some hair. We've also gained a little nano Kempa here, which has made our days a lot brighter. His name is Luca. That's Tom's son. But throughout all these changes, as you can see in these photos, is a steadfast constant. I don't know where I was. Oh, he makes up the foundation of this lab, and his name is Tom Kempa. Because of Tom, the Kempa group continues to exist as a family of the best, brightest, and most caring individuals with Tom at its center. I am beyond lucky to have been welcomed into this family back in 2017 and to have found in Tom a mentor not only in science but in life. Tom, you have taught me more than I can ever say thank you for. I can never fully find the words to express my gratitude for all the time, support, guidance, and friendship you have shown me over the last few years. I will miss our monthly catch-ups, heart-to-hearts, and chats, and I can only hope that I have made you proud, and I hope to someday make the same impact on others as you have made on me. My goal is to make him cry so hard that he can't ask me questions. To the members of the Kempa group, I could not imagine better people to have spent my time at JHU with. Dara, Reynolds, Ja, Ona, Ife, Catherine, Paul, and Ambar. Whether I have known you for 1 year or multiple, you have all pushed me to be a better scientist, lab mate, mentor, and person. Thank you all for making my time at Hopkins what it was. To former Kempa group members who paved the way before me, you can see that I'm crying talking about you. Dr. Tamoja Chowdhury, Dr. Eric Sadler, Dr. Jamie Claire, and Eric Thompson, who's here. Thank you for being my warm welcome into this lab and into this family, for making every day full of laughs and learning, and making Hopkins feel like home. Sachi, thank you for showing me true friendship during some of my hardest times. To Dr. Ben Stevens, I can see you. Thank you for showing me for your mentorship and guidance from the first moment I stepped foot on campus. We truly did make the best team. I will always treasure your kindness, your warmth, all you have taught me. The 17 times I asked Ben to have coffee with me to determine if I wanted to join the Kempa lab, when I was even a question, that was all because of him. Along with Ben, Alex, and AJ, thank you for teaching me all I know about nanoparticles and making every day in the lab one that I could look forward to. We definitely had a lot of our laughs. This body of work would not be possible without the groundwork you laid and all the knowledge you shared with me. Dr. Marina Solomos, thank you for being such a brilliant mentor and role model to me and others in our lab, and for always reminding me to trust the process. I will cherish our time together when you were here, which brought a new, dear, and lifelong friend into my life. I'm so proud to know all of you, and I'm so proud to know about all of your amazing achievements. To my friends that I've made, oh no, this was supposed to be up while I was talking about that, but it's fine. So we have some beautiful pictures from Ben's wedding, holiday parties. This is the last Halloween, ice skating outing, and there's our little Luca in the center. This is our superstar. So to my friends that I have made through JHU, Jesse, John, Mike, Dana, Austin, Paulina, Brandon, Sim, Kristen, and Kristen, I and me. Thank you for all the fun times we had and the memories you made with me in Baltimore and beyond. I'm so proud of all that you are all doing as well and achieving, and I can't wait to hopefully reunite soon. Outside of the chemistry department, I was lucky enough to cross paths with some more people who I quickly realized were in that category of my people. He's making me look better, you know? To the Higher Hopkins team, Aaliyah, Emma, and Chris, thank you for giving me an opportunity to grow and learn outside of this PhD program. Every single day, you all teach me new skills. Chris, thank you for showing me that no task is ever too hard to tackle. Your determination is unmatched. Emma, you've made me more deeply appreciate being able to think on my feet and be prepared to solve any situation. Your kindness and awareness and positivity are traits that I strive to have. Aaliyah, thank you for showing me what it means to lead every day full of passion and positivity as well. You've all challenged me to go beyond my comfort zone and expand my skills every day. Above all, thank you and everyone at LDL for making the important work that we do fulfilling and also fun. I will always be grateful for our time together and the doors this office and work has opened for me. Can't look at you for this one. So another truly amazing group of people that I got to know and work with here at GHU is the Futures team. Tyler, Desmond, Randy, and Meg, it has been such a pleasure to work with you, to learn from you, and to trailblaze through changing how we support PhD students and postdocs here at GHU. You are all such talented and inspiring individuals. Gian, who's off changing the world at his new job at BCG, he's my work husband. It's consensual, he called me his work wife at his PhD defense. I could never thank you enough for all that you have taught me, for countless hours preparing me for job interviews, and all you have done for me, for other students, and for so many communities at Hopkins. I'm proud to know you and feel so lucky that our paths crossed here. Roshni, thank you for showing me what it means to lead with lasting impact, but also with empathy. I feel like I'm yelling at you. I once described you as a tree with roots that nurture the many who encounter your branches. You in this office have impacted so many people's lives and nurtured their futures, with mine being one of them. I'm so grateful that we met back in 2020. I'll always be here to cry, sing, and laugh with you through the good and bad times. Thank you for showing me how to find strength in the struggle and for creating something so special that I could be a part of. Dr. Farouk Day, thank you for bringing both of these offices and these people to Hopkins. Your thought leadership and support makes all the work that you do possible. Okay, so the people I haven't necessarily found while I was here, but I've always had in my corner. Some of you have made the trip here from New Jersey and took time off from work and school and your daily lives, and I'm so appreciative. Thank you for your unconditional support. I can't see my comment here. For understanding my absence for so many important life events like baby showers and birthdays and weddings, but for welcoming me without question when I was able to make that trip and be present. Your support means so much to me, and you'll never understand how much it does. That doesn't make sense. Milena, who's sitting all the way up there, I can't look at her. My oldest and loyal friend, this picture was taken in, I think, 2001. Thank you for always being only a phone call away. Your ability to know when to simply listen, when to give input, and when to call me out on my absolute nonsense is unmatched. Thank you for also reminding me of my courage when I lost sight of it. We've been friends for 24 years. I'm only 29, so it's a long time. But cheers to a lifetime more of that friendship. You can't look here now. Jeffrey, my partner and my rock. Thank you for helping me when I didn't know how to hold myself. Why are you recording this? You've helped me through some of the hardest challenges I've ever faced, and you make me feel that I can achieve anything. Jeff and I, for those who don't know, have spent the entire duration of my PhD long distance with him back in New Jersey, which is exactly 131 miles from my apartment to his front door. It's a whole lot of driving and miles. Over the last few years, that physical distance has tested us, but I have never felt that you weren't right with me at every step of the way. You will always be the first person that I want to share my news with, whether that's good or bad. I am forever grateful to you, for you, and I cannot wait to see what we will achieve together in the years to come. Home is wherever we are together. Okay, now I can't look here. To my siblings, Pasha, Martin, and Michal, thank you for always being my support system and for creating the absolute lights of my existence. Adam, Oliver, Emily, Ava, and Max. To my sister Kathy, especially for being my second mom, my lighthouse in the dark, and my best friend in the world. She walked me to school on my first day of pre-K 25 years ago, and she's here today on my, what I call last day of school ever, hopefully if Tom lets me pass. 25 years later, that's 86% of my entire life for those who were wondering and wanted to know the math. The fact that she's here has a lot to do with her unacceptance of the words, "I can't do this," whenever I uttered them. Thank you for always reminding me of my strength and for showing me what it means to be strong. I will forever be grateful for your support, your existence, and that we were made to be sisters in this fight. Okay, this is when it gets really bad. To my parents, last but not in any way least, I owe more thanks than I could ever give to my parents, Andrzej and Barbara. This is a true story. My dad came to this country a little over 30 years ago with nothing but $100 on loan in his pocket. Along with my mom, he turned that $100 into a home, into opportunities, and into a new life for my siblings and for me, and now their grandchildren. Mommy, please don't cry. No thank you will ever be enough for that act of absolute alchemy and the sacrifices they have made, leaving behind their homes, parents, families, support systems, language, and comfort from one set of struggle and knowingly walking into another to give their children and grandchildren the beautiful lives that we lead. When they had nothing, they gave us everything, and for that, I owe them everything. My parents are my models of resilience and determination. They taught me the importance of hard work, self-improvement, culture, and loyalty. They pushed me to always strive to be the best version of myself. They are my guiding light and the reason I do all that I do. They are my heroes, and I'm so proud to be their daughter. Mamo i tato, zawdzięczam wszystko w tym życiu wam. Jesteście moimi wzorami odporności i determinacji. Dziękuję za poświęcenia, których dokonaliście, aby zapewnić swoim dzieciom i teraz wnukom piękne życie. Dziękuję za nauczenie mnie, jak ważna jest ciężka praca, samodoskonalenie, kultura i lojalność. Dziękuję, że motywujecie mnie do ciągłego dążenia do bycia najlepszą wersją siebie. Jesteście moim światłem przewodnim i powodem, dla którego robię wszystko, co robię. Jestem dumna, że jestem waszą córką i dedykuję wam tę pracę doktorską. So I don't know if you'll notice, but the orange bullets on my slides are in Polish, that my parents could at least a little bit understand why they're here today.
So you must another cry.
So I thought it was fitting to end this presentation with a picture of me on my first day of school in September of 1999. I wanted to give a little special shout out here to all the teachers and educators I've ever had in my life, in their many forms, in the classroom, on the field, and on the stage. Some of whom are here today. Miss A, she's my high school chemistry teacher, and Miss Warzepa, she's my high school Spanish teacher. My pre-K teacher is online, who literally taught me when my sister walked me to school that day. Thank you all for supporting this little girl's mind, creativity, and passion for learning. You fostered my love of knowledge and led me to where I stand today, and I hope I made you proud. All of you here, those that I've mentioned, those on Zoom, you've all helped this little Marty find herself. I'm truly, truly overwhelmed by all the support, and I thank you again for your time and for sharing today with me. I'll now try to answer some questions that you have. Oh.
Marty, you're only wrong about one thing, and that's that I didn't break.
You hide it very well, unlike me.
Yeah, I know. It was tough. That was, thank you so much for what was an elegant, clear, and compelling thesis defense, and also, I mean, and eloquent at all stages, even at the very end. Basically, exactly, like letting your part out. I actually kind of, so I was tenured not too long ago, and I didn't really have a chance to sort of let it fully sink in, and in some sense it actually did when I was just listening to you over here, because when you showed the photos of our group evolution over time, and then all of the very emotional and intellectual attributes of essentially running a group, I realized that actually I would go all 50 times if only for the opportunity to bring together a lot of really fantastic minds and hearts basically together and to be able to witness moments like this. So every single one of those hair follicles that I lost was damn well worth it, and I lose it again.
I was like, Jeff, should I bring it up?
Do you hear that, Ken, wherever you are? So it's like, it's the currency, and I'll gladly tear all my hair out so we can keep doing this until the rest of basically my time on this planet. Honestly, thank you so much. beautiful, elegant thesis defense. And yeah, and I think that you're the only person I've ever seen who's actually given thesis defense slides in 2 different languages. And let me tell you, for those of you who are not Polish speakers or capable of writing, it is very non-trivial to speak in technical terms in a language that's not technically your mother tongue. I know that for a fact too. I once had to give a talk in front of the Polish Academy of Sciences, and I literally had to, and I'm a native Polish speaker, I literally had to practice for about 2 weeks, like nonstop, just to be able to do it. So the fact that, yeah, anyway, really well done. The floor is open. The way this works is the floor is open to questions from the public. We on the committee don't say anything, and then we're going to ask you guys to please step out, and then we have our own private session with Marty.
Everyone is welcome after questions to head down to room 140, which is just downstairs. There's beverages, snacks. Please eat, enjoy, relax. Hopefully I won't come in crying for other reasons. But, you know, if I keep joking about it, it won't happen. But please go downstairs and enjoy it. But I'm happy to answer any questions that any of you might have.
Floor is open.
If not, it's okay. No, you're showing emotion. Yes, Dr. Carlin.
Okay.
Oh gosh, that's a bad sign.
Can you go to the first, the last conclusion slide? To make the question easier to ask. That,
Oh, sorry. Almost there.
yeah,
I'll put all the figures up.
so my question is that the silver bromide nanoparticle start with, when you form the silver ion bromide ion,
Right.
how do you don't know anything nano, how do you make it nano? How do you prevent it from, how do you make it spherical? How do you prevent it from sending long distance?
Into longer scope.
Yeah, a little outputs.
So that is all thanks to and due to that stabilizing oleate ligand that we introduced into the solution. So at the solution pH, they formed a nanoscale. My cell also very favorably interact with that silver bromide surface, and in that way we quickly stabilize the nucleus of silver bromide within the solution with those oleate ligands when they're made. So we basically add the precursors to a highly concentrated solution of those oleate ligands.
And then
Backwards.
when you make the so-called,
Sorry.
the silver bromide, silver, you call dimer,
Yes.
they're reducing it and you're adding reductant. But so the silver solids, metallic silvers, zero valent silvers coming at the expense of silver ion and silver bromide.
Correct.
So isn't there a loss in size of the left hand valve as the right hand valve gets bigger?
There absolutely is. I do have some data. Maybe not. Oh, right here. So as we grow that silver bromide dimer, there is a slight contraction of the silver bromide phase, especially when it goes from that cubic morphology to that spherical morphology, and then the growth of the silver phase of the dimer. But at the end of that process, they are roughly the same size. There's only about a 2 to 5 nanometer discrepancy between their diameters. If we continue to irradiate them, the silver continues to nucleate out, and then the silver bromide actually totally contracts and disappears, and we get this sort of silver rod-like structure, which I can show you if you want to see. Yeah, absolutely. Anything else? Yes.
Kind of building off of, I was just talking about what keeps your nanoparticles the first to the side. There's this ligand on the outside layer. When you go then to your catalytic testing, have they been prepared in some way, or are you testing it with that?
Yeah, so the catalytic particles are not coated by the oleate that's initially coating the silver bromide. When we dimerize and form that silver bromide dimer, all these beautiful pictures make me feel better. So I just didn't include the ligands for clarity here. So there's oleate and ascorbic acid on the surface. When we dimerize, we suspect or are pretty confident that that oleate and silver bromide do not migrate to the silver phase of the dimer. They're staying on that silver bromide. So this is ligand free. So we can selectively coat those particles with a different ligand like CTAB or citrate, but there's capability for us to have simply silver nanoparticles that are ligand free, one of them too. We do coat our silver copper alloys with CTAB because if we don't, they sort of crash out and aggregate in solution, which again confirms that there's likely no ligands on the surface, but that hasn't hindered our catalytic activity. I actually think the CTAB is more so forming like solution phase micelles around these particles as opposed to actually interacting with our surface. So when we spray or airbrush them onto that carbon substrate, there's probably just loss of ligands. We also perform purification steps and concentration, so there's also removal of ligands there too. That's a great question.
I think we have time for one more question. Anyone?
Oh, Ben.
Oh yeah, people on Zoom.
Ben, yeah, can you hear me?
Yeah, sorry, I think there was an issue on my end. First off, congratulations on a wonderful talk.
Thanks, Ben.
Great job. Second, it seems as if you're able to dope the precursor silver bromide with copper cations in the resulting phase, even if there's a drop in the copper concentration from the nominal doping. The concentration of the final product will still have an ever-increasing amount of copper. Is there a certain endpoint where this plateaus or a point where the synthesis breaks down when copper it begins to interfere too much?
Yeah, so that would most easily be explained by just that 15% copper incorporation limit. So once we start, I actually never redid these experiments, but previously when these copper silver systems started to be experimented with, that 12 to 15% copper incorporation was our higher limit. And at that point, there was likely higher degrees of copper oleate complexation and therefore lack of stabilization in those silver bromide hosts. So there definitely is an upper limit, and it is much lower than 15%, as we can see in our ICP-MS and EDS calculations. Does that answer your question?
Thank you.
Yes.
Absolutely.
I guess Catherine said she had a
Yes.
quick question.
Yeah, it's also related to the copper stuff, which is really interesting. I guess I'm just wondering if you think it would be possible to start with a copper bromide like species and selectively pull out the copper as like, and then, you know, maybe incorporate silver with the silver cations. And also just generally, like if this could be also used with like gold or something like gold bromide, like if you think that is transferable.
Yeah, so that's a great point that you bring up. The next probably sets of materials that we would look at in terms of incorporating into the silver bromide lattice would be gold, just because it's relatively easier to make gold silver alloys. I say that, but it's really not easy at all, and potentially platinum. I've never thought about starting with my host. I would maybe be a little bit concerned about oxidation, so there'd definitely be some sort of ligand manipulation and engineering that have to be done, but I don't see why not, especially if it's hosting those cations interstitially. The reason we do use silver bromide though is because of that photographic effect that Tom mentioned. These materials since the early 1900s have just been well known to produce those silver nucleates, which make photographs that we see. So, I mean, if I had 17,000 years, I would do all of this, but that's actually a really good point. Thanks. Yeah.
Okay, thank you very much. Thank you, Marty, again for a fantastic talk.
Thank you. Thank you to everyone on Zoom. I'm going to now close the room for the private defense portion, but it's really great to see you all, and I'm so thankful. And I'll talk to you all soon.
Marty, you're right. Right.